I am a machine learning engineer at a company called Weights and Biases. Uh, it's an MLOps platform, and it's like industry standard at this point of time for doing anything MLOps. Um, Other than that, I'm also a Google developer expert in machine learning, specifically in TensorFlow. And I'm also a Kaggle master in the notebook section. And I'm like pushing hard to be like an expert, at least in the competition section. Having said that, I have been doing machine learning for the last 5 years now. And here I'm just gonna be trying to unbox large language models. So this talk is basically inspired by, I guess, almost all of our heroes, Andres Karpathy, and he gave a nice talk on Nano GPT. Like he basically created a nice YouTube video, let's build GPT from scratch in code spelled out. And this video has almost like 3 million views right now. And yeah, it's a very popular video, and a lot of folks have tried this out, have played with the code, experimented with this. But this is a very simple implementation, and most importantly, a very readable implementation of large language model. In this case, a GPT-2. So what is a language model? A language model is something, I'm not sure if you all, I'm sure kind of like you all might have heard of and played with ChatGPT, at least at this point of time, wherein there's a with which we can do some sort of conversation, right? So you're writing something like hi, and then it will give you a response like, hello, how I can assist you today. So what a language model here is doing is when you give some initial text, it starts predicting the next text, right? In technical terms, these texts are called tokens because, I mean, we don't put in raw strings or raw text to a computer. It cannot process a raw string, right? It has to be converted to numbers. So the numbers are called tokens, and I will touch upon that point later on. But the point is, a large language model basically takes in some starting point, and then it starts predicting the next point, right? This is a classical generation style LLM task, right? So it can help, like we can do the conversation here. Like it's a very advanced, highly production grade system that's out there. But today, what we're trying to do is we're gonna be inspired by this talk by Andres Karpathy as well, GPT. We're gonna be basically going through the entire like architecture design plus the implementation of a GPT from scratch. And I will be touching upon the nuances, some of the nuances of a large language model, or language model for that matter, right? So here we'll first start with a very simple baseline few parameter model, and then we'll slowly add upon few of the recipes that were developed in order to like use or trade a very big, powerful generation model, a language generation model. So I'm not sure if you all have seen this, but if you can see my screen, this is the most standard paper. Attention is all you need. I'm not sure you all might have heard of this paper at some point in time, but this paper introduced the architecture called transformers and introduce a very important component called self-attention or multi-headed attention, right? So we're gonna be trying to implement this section of the architecture, which is called the decoder section. And so like in a conventional, like the paper proposed encoder and decoder style architecture because neural translation was a thing back then, wherein you give some text in English and you generate the same text in French or Spanish or some other language, right? So translation was a thing back then. Now, like it has been like what? It was released by 2017, so it's been 6 years now. And a lot of development has been done in this field. So decoder style model is widely used architecture design for generation tasks, right? And I will touch upon encoder style a bit later in the session, but let's focus on this. So as you can see in the architecture, we start with some, let's forget this output. Let's start with some input. We embed the input. So there's a concept of embedding here. There's some concept of positional embedding or positional encoding. There's some attention blocks. There's some skip connections. So as you can see here, this is a skip connection, some addition, normalization, linear, software, etc. It's like fancy thing that this architecture is, but we're gonna break it down, right? So let's go to the let's go to this collab and let's start running through it. Okay. So what I'm doing here is I am basically using a data set called Tiny Shakespeare. This data set was also compiled by Andrej Kapathi, and this data is basically the compilation of all of the text of Shakespeare that you can find. And yeah, this is like some 1 MB worth of data, and we can read it. Let me see if I can open this file in here for all of you. Input.txt. Yeah, so this is like Shakespeare, right? First citizen, before we proceed any further, hear me speak, all speak, speak. So like this is like a nice thing that was written by Shakespeare. And you can see there's like many lines of text in here, right? And we're gonna be using this to train a language model, and such that language model starts generating text in Shakespeare style, right? That's the idea here. So, and feel free to interrupt me if anyone has question or anything. If I'm going fast or anything, just let me know. Okay. So yeah, we read the text. Let's look at the first 1,000 characters in the text file. So I actually showed you kind of an entire file, but these are the first 1,000 characters in this text file. But there are a total of, I guess, over 1 million characters in this text file. So why I'm saying characters and not words? Because the language model that we're gonna be preparing or training or building is gonna be character level language model. It's not gonna be a word level language model. So what I mean by that is when I give F to the language model to start with, the next prediction should be I. And when I give I, it should predict R. And when I give R, it should predict S, right? It should go like this. When you give some character, it predicts the next character. You give the predicted character back to the model, it predicts the next character. And it goes on. So that's why this is a character level language model, right? The language models out in the world that we use, that we interact with on a daily life, for example, the ChatGPT, these are word, actually sub-word level language models. So like a sentence is divided into sub-words, and there's some clever ways of doing so. And that division is something called tokenization. I will touch upon that real soon here. But yeah, so first we need to know all the possible characters that can be found in this text file, right? Why do we need to do so? Because any deep learning model, any model for that matter that we train, or any neural network-based model is like a probabilistic model, right? You need to find a probability distribution over something. So you need, in this case, in a language model setting, you need to, the model is basically predicting what the probability is for every character that might exist in this text file, right? So we need to get the number of like all the unique characters. And like, yeah, I hope you all are familiar with Python and you are coding in Python. So set is a very nice function here that can, like just give you the exact unique things or elements in anything, like any list or any string. So if I run this, you can see that there are a total of 65 unique characters. The first unique character is basically a new line. So you see a new line here, and I have not provided any /n in the print statement. So this new line is coming from the characters, because I have kind of joined all the characters because they are string, I can join them together. So first character is a new line. The second character is a space followed by an exclamation mark, dollar sign, and percent, etc., etc. And then we have all the capital alphabets followed by all the small alphabets. So these are 65 unique characters that's in this text. So our language model will be, for a given character, say we start with a blank space or we start with a new line. For the given new line, the model will then predict what's the probability. I mean, it's going to be finding the probability distribution for all the 65 characters. And then it's going to be finding which has the most probability. And then based on that, it's going to be predicting the next token, right? So after a new line, if the probability distribution says that A has the most probability, then it will generate A. And then new line plus A, it sees that, and then it will look, just again, derive the probability distribution, and then it will sample one from that. And this is how it just keeps on doing so. Now, at this point, we know what are the different unique characters we have. We will be converting strings or raw text to integers. And this process of converting raw strings to integers is tokenization. It's very simple, right? So again, there are many ways of doing tokenization. We are doing a very simple tokenization where we are simply converting every character. So for example, F will be converted to an integer, I will be converted to an integer, R to an integer. So if there are 1 million characters here, there will be 1 million integers, right? And I mean, the integers will range from 0 to 64 because there are 65 total characters. So these are some simple functions here. So we run through the entire unique characters, and then we basically create a table thingy here, right? So character has been mapped to an integer, and in a different dictionary, we are mapping the integer back to character. Why? Because we want to decode the text, the strings, or the characters to integers, and this function will do that. And then we also want to have a function to decode the strings from, decode the integers from integers to strings. And this is what's been done here using the function. So we have tokenization here. Let's see. Yeah, there are some other fancy tokenizations. For example, the sentence word piece tokenization, and then some sentence piece, etc., byte pair tokenization. There are many fancy algorithms out there to do tokenization. Again, let me ask ChatGPT. Yeah, so white space tokenization. So you break like any given text file into different, like every white space has been split. So every word, it's like a word level tokenization, like another kind of word level tokenization. I think it's going to be very poor. Then this is also word tokenization, sentence tokenization, subword, character tokenization. This is what we are doing right now. Yeah, again, n-gram, etc. There are so many fancy tokenization schemes, and yeah, it's good to learn them and try to implement them, and yeah, see for yourself what works for you for your given problem or task. Again, there's no one silver bullet. You need to try things out. So what I'm doing here is this piece of text, hi there, has been converted to integers. So 46 is for H, 47 is for I, 1 is for this white space here, 58 is for T, so on and so forth. And then we can decode it back from the encoded text to which will give this list of integer. And then if you use the decode function, we get back the string, right? Great. So this is tokenization. So by now, we basically loaded some data, some text file. We derived the vocabulary, which in this case are the 65 unique characters, because it's a character level language model. Then we tokenized it, basically converted the raw strings to integers. using character level tokenization. And now, and because this was just list, and we want to be training some model, so we need to convert like list to something, to tensors, right? Because they can do then, we can then send the tensors to a GPU using CUDA, two devices, right? So we can do those fancy stuff. We can train using GPUs and all. So if you see the first 1,000 characters in the text file, this is what you see. So 18, 47, 56, 57, etc., right? This is the first 1,000 characters in the form of integers, and this is equivalent or exactly equal to this. So if I decode the first 1,000 ends, let me see if I can do that. ToList will give me the list, and then I can do something like decode ends. Yeah, let me give a fancy print statement as well, so that they look same. Right. So as you can see, this is exactly the text that we saw before, right? So this is us tokenizing the raw text. Now, in any machine learning problem statement, we need to we need to prepare the data. We do some pre-processing, in this case tokenization. Then we split it. Okay, so we split it into train and test. We are using 90% of the total data as train data, and the rest 10% as the validation data. So you can see the numbers here. So we have some 100K examples as validation and 1 million as train. Great. Now, obviously, we cannot pass the entire sequence or the entire data to a model. We cannot process 1 million integers at once, right? We need to chunk it. So this is what the block size is doing here. We are taking a chunk size of 8. So if you see here, this is the train data, and we take the first 8 plus 1 characters, or 8 plus 1 tokens. Yeah, but for going forward, I will use the term tokens instead of characters, okay? Because we have converted characters to tokens. So there are 9 tokens here. Let's forget about plus 1. But what it's basically saying is that if the first token is 18, then the model should predict the next token to be 47. If 18 and 47 are the first 2 tokens, then the model should predict 56. If 18, 47, 56 are the first 3 tokens, then the model should predict 57, so on and so forth. If the model sees these 8 tokens together, 18, 47, 56, 57, 58, 1, 15, 47, the model should give the most probability to 58 to be predicted, right? So you can imagine from this example that in one single chunk, there are 8 examples packed. How come? Let me show here. So we have some x, which is 0 till the block size, and then y is offset by 1. Because we are predicting the next tokens, we need to offset by 1. So that's the ground truth, or y, right? So now let's spell it out. So if 18 is the first token, as I said here, the target should be 47. Similarly, if 18 and 47 are the first 2 tokens, then the target should be 56, right? So if you have done image classification, you know that if this is an image of a dog, then the target is some ID 0 or 1. If it's a cat and dog classification, the dog can have an ID of 0, and the cat can have an ID of 1. So that's like a supervised learning, and this is the same thing. So for this, you have the target this. So you need to, you basically are finding a probability distribution over the given input, and then you're just mapping it to some output, right? So that's how you are spreading it out. So the point is, for one given chunk, so for one given example or chunk, we have 1, 2, 3, 4, 5, 6, 7, 8, 8 examples packed in it, right? And you can see how this is one example in itself, and this is another example in itself, right? Great. So this is one example, but to make, to leverage GPUs, because GPUs are really good with parallel processing, we need to provide any model batches of chunks, not just one chunk, right? So this is a nice function to, again, like get a batch of any batch that we specify. So you can see that we are basically, finding some random ID of size batch, a random ID, and then we are basically going in the train data if we are selecting a train data as the split, or the validation data if the split is well. So we then randomly pick 4, if the batch size is 4, we randomly pick 4 chunks from anywhere in the whole corpus. So this entire thing that is showed here, let me remove the whole thing. Yeah, this is the first 1,000 characters, but this is like a whole corpus. This is like 1 million such tokens, and that's the whole corpus. So you basically go into the corpus, pick randomly from a spot, select first 8, and then 1 plus 8, like offset by 1, and then X and Y. That's your X and Y, and then you basically return that. And that's your batch, right? So the batch size here should be 4,8, right? Because the block size is 8 and the batch is 8. So let's look at XB and YB once. So this is XB, right? So 57, 146, 47, 57. This whole thing is a piece of chunk from the corpus. And if you look here, this is the Y is been offset by 1. So 57, if the input is 57, the output should be 1. If the input is 57 and 1, the output should be 46. If the input is 57, 1, 46, the output should be 47. Thus, when we take a batch size, say of 4 and a block size of 8, there are basically 32 examples packed, right? This is like a very clever way of getting most out of your training. Very clever way of packing stuffs together. But yeah, this is how you do it. And the dimension here is basically batch size, comma T. So T here is the time or the block size, or you can also call it context length. Context length is a more newer term that we use right now. But yeah, either a block size, context length, time, sequence length, whatever, same thing. Now let's build a simple bigram language model. And at this point, I would like to take a pause. And if anyone has any question, any confusion, do let me know, and I will love to resolve that right now. I think we are good to go. Right. So it's a very simple bigram language model. Let's forget about the bigram part, but let's just focus on a very simple language model. So what this language model is doing is taking some IDX, and IDX is the input. So IDX is this XP, right? So this XP, this is basically taking this, and then it's passing the IDX to this table. So what is this table? It's an embedding. It's basically a vocab size by vocab size. So vocab size is what, 65, because we have 65 unique characters. So that's the vocab size. So we have a table vocab size by vocab, or 65 by 65, right? So what it's doing is, so whatever, say if the IDX is 57, then it's in this 65 by 65 table is going at the 57th row and picking the vector there and returning it back. Then it goes to the first row, picking the vector there and taking it back. Same 46, 47, it just goes there in the table and pick the vector back. That's what it's doing, right? So this NN embedding is basically a very thin wrapper around this table. So let's run this, and I will love to show what's actually happening inside this table. But if you run this, you can see in the forward method, we pass the input, we get the output or logics. And as I said, this logic is nothing but just going in that row, in that 65 matrix, going in that row and picking the vector in that row. That's all. So obviously the shape should be 4, 8, 65. 65 why? Because the table or the vector that is plucking out from the table is of length 65. That's why. And 4 is the batch size and 8 is the tokens in that chunk, in that example, right? So this can also be interpreted in this way that for every token, so for every token, 57 is just an integer, right? But we can represent 57 using some high dimensional vector or embed, and which is called an embedding, basically. An embedding is nothing but a higher dimensional vector which presents some dimensionality. Right? So 57 is being represented in a different space right now. So if I just look at the first batch, and there's like 8 tokens, right? If I just look at the first batch and the first token, it's a 65 dimensional vector, and this is basically, and let's actually look at what that vector is, what that token is. 0. Don't think. Oh, sorry. This is going to be XP. XP of 0 and 0 is going to give me that token. Right. So the first IDX was 57, and that is being represented with the 65 dimensional vector. That's all is happening inside this model right now. So
Ayush, just one question more. So can you elaborate just about vector mapping again? Like how actual vector mapping works actually? Yeah.
You mean what's happening inside this model?
Yeah. If possible, like yeah.
Okay. So as I said, I mean, this is a very simple model. Let's start from this point. We have some XB, which is the input, and we have the YB, which is the target, which is what the model should be predicting. So this is basically an input of batch size 4 because there are 4 samples, right? So batch size 4, and every batch has 8 tokens. So the context length is 8. So 8 tokens in every batch, right? So if I give IDX as, like, if I give one ID as 57 here, I mean, you can imagine that, and we are passing the whole batch to this table basically, because self.token embedding table is this thing. So if we are passing the whole batch, because that's what's happening here, it's been passed to this whole thing. So what's happening inside, right? That's what I'm trying to explain. So internally, so let's initialize the table separately, okay? So this is the table of vocab size by vocab size. So 65 by 65 other size. So the table is 65 by 65. So obviously it's a neural network, some wrapper around it. So it should have some weight as well, which we optimize for, right? So the weight should be of shape 65, 65. Right, so it's 65, 65 because that's what the weight is going to be. Let's keep the weight here. Now let's pass ID. So here we are passing IDX, which is the whole batch, but internally it's basically picking the first and the second, the third, fourth, like separately. So let's pass one as the ID here, and let's ask it to return some higher dimensional vector embedding in this case. So this is for 1. That 2 is being represented in a different way. So 2 is being represented by 0.4106, 0.5051. Obviously, it's different from 1, right? And there are 65 unique vectors like this. So every integer is being represented by a vector, and that's exactly what's happening in here.
Just correct me if I'm wrong. Or suppose for every encoding that we did, we are generating different. You can say, how I can say, for every encoding we have different tokens, and to make it more, you can say, how I can explain that, to make in the range of, so that it is can be understandable from the machine from 0 to 1 concept, like that we did in I guess fashion MNS data set. Like we are basically converting that to, like, the range is from 0 minus 255 to 255, sorry, 0 to 255. So we are making the range to 0 to 1. So I'm just understanding this is the same concept that we are doing, like converting that into majorly to a very small interval, so that it can be understandable by the machine, or it's something like else. Like if I'm
See, the machine understandability part was taken care by tokenization, right? So raw strings has to be converted to some numbers. So that was taken care by tokenization, right? So the
okay,
tokenization gave us some integers, right? But these
got it.
integers in itself are just, I mean, it's just, I mean, what we are doing is basically representing every integer. Imagine this to be not a character level model. Imagine this to be a subword level model. Okay, so there might be a vocab size of 50,000. So there might be a 50,000 vocabularies that's possible in your given text, right?
Got it.
Now, every subword, I mean, whatever token you have, you want to represent that token to a higher dimensional vector. Okay, because a higher dimensional vector will have more power to represent the underlying data compared to just an integer, if I'm
Okay,
making
got it.
sense, right?
Okay, yeah, got it.
There's like 65 numbers representing one integer, and obviously an embedding is something that is being trained while the optimization goes on, right? So
Got it.
embedding learns the best way to represent that token. Okay, so
Okay,
that's what's happening here.
got it. Got it. Now
Okay,
yeah.
yeah. So this was a simple language model, which basically was nothing but returning some higher, like basically converting the tokens to a higher dimensional vector and returning that. Great. Now we need to compute loss, because as you see here, we are just passing the inputs and returning some logics from there. We are not computing any loss here. We need to compute loss. Given it's a supervised learning task, we have some ground truth targets, we can do loss computation, right? So it's the same thing. Getting the logics, but we are also computing a cross entropy loss in here. Why cross entropy loss? Can anyone answer that? Like how? I mean, how can we just get by building a language model and using a very simple cross entropy loss? All those who have trained an MNIST classifier or any image classification have done an image classification task, they might have used a cross entropy loss function, if I'm correct. So what is cross entropy doing? Cross entropy is basically saying that, okay, these are the probable classes that's present. If the prediction is close to the target, if the prediction is exactly the target, then the loss should be 0, right? And if the prediction is very far away from the target, then the loss should be very high. The cross entropy is basically giving us helping us find the exact like predictions that's corresponding to the target. So we are using cross entropy a lot, and you can imagine, like in an image classification task, we have say 10 classes. So cat, dog, plane, car, bat, ball, etc. Like say 10 classes. We use cross entropy loss there. Here also we are fixed by the vocab size. We in this case we have 65 as the vocab size, so there are 65 classes. So we are doing the predictions over the 65 classes. We are just finding the probability distribution over the 65 classes. That's it. So we can get by using cross entropy loss. So we compute the loss.
Ayush, I guess
Yeah.
there is a more question from Harsh. He's saying, can you please give a reference for cross entropy?
Reference for cross entropy, as in they want to see the formulation, or
I guess he's just about formulation only, I'm guessing. But in case Harsh, if you didn't know, like cross entropy is just kind of activation function, just to basically help our model become better, I guess. Yeah.
Yeah, it actually comes from the information theory. Like all those who have done ECE or information, I have studied information theory. Cross entropy is coming from there. So it's like we take through the probability distribution. So if you see here, the logits is a probability distribution, and the targets is also, like you can imagine targets to be probability distribution, right? So the cost entropy is basically taking two probability distributions and measuring the average number of bits needed to identify an event. So it's basically saying that, okay, there are two probability distributions, find how similar they are in a very layman term. And if they are very similar, then the loss is very small. If they are not very similar, they are far apart, then the loss is very high. That's what cross entropy is doing. Right? There are a lot of good articles that you can find on cross entropy loss from the mathematical perspective. I highly recommend check that out.
I guess Harsh is from second year. So Harsh, I guess in engineering mathematics there is all, or in 11th, I guess you learn about the normal formula P plus Q equal to 1, which is basically the probability distribution kind of thing. So that's the basically concept. Otherwise, like you can go to the documentation or official documentation, you can check it out. Yeah. I just want to add that thing, Ayush. Yeah.
Thanks for that, Karthik. Yeah, so we are computing the loss function here. Let's run this. Now we are returning the logits as well as loss. Again, the logits are nothing but in this, like till now, logits are just the higher dimensional representation of the tokens, right? So what's the loss? So loss is 4.5170, right? So that's the initial loss that we have. The model, I mean, there's like nothing we have trained, anything, but for a batch size of 4 with a context length of 8, if we pass to the model, we get the loss of 4.151. And we can kind of guesstimate what a loss of any such model which uses a cross entropy by using the simple formula, like negative log of the reciprocal of the number of classes. So in this case, the number of classes is 65 because the vocab size is 65. So 1 by 65 log of that and negative of that will give, I guess, 4.17. So the initial loss is very close to our loss, right? So, I mean, this is also a recommendation from a best practice point of view, that whenever you are building any classification-based model, or any model for that matter, which uses a cross entropy as the loss function, you can guess what the loss is. And after passing a single batch, if your loss is somewhere close to the guessed loss, you can consider that your model design is correct. There's no flaw in that. So yeah, just wanted to throw it out there. Now, so far, we built a simple model. We added a loss computation part to the model. Now let's add a generation method to the model, because at the end of the day, once we have a trained model, we want to use the model to generate text in the Shakespeare style, right? So what we are doing here is we are getting the inputs and passing the inputs to the model. So the self IDX is basically calling forward IDX targets, right? So we pass it to self IDX, we get the logits. Logits again here is the higher representation, but we'll leave it to that. So we can get the last token. So if the first, if the IDX is of bad, if the IDX is B, 4, 65, the context length is B, 8, or 4, let's call it 4, 8, 65. That's what your logits should be, right? Because your batch size is 4 and your token size or a context length is 8. Since it's a simple model, what we are doing is whatever token the model has seen previously during generation. So if it has seen, say, 4 tokens, which means 4, which is the batch size, 4, which is the number of tokens it has seen, 65, we pick the last token, which is the 4th token here, right? So -1 is giving me the last token. We then get the representation. The logis is the higher representation, higher dimensional representation. So the logis becomes batch, C. We get the softmax. If you have trained an image classification model, you know that there's a softmax layer. What it does is basically, given a probability distribution, it basically pushes the one which has the most probability higher than the rest, which makes it very easy to pick that as the most probable class. So we use a softmax, and then we basically sample from the distribution and just get like an ID. And basically ID, like the sampling is nothing more than, say, in a row, in a vector or the number of classes to be 65, if 57th has the highest probability, then we'll just return an ID 57. And we know, and we just concatenate it back to whatever tokens it has seen. So that's all generation is. Again, generation is not the core point of this session. The core point is what are the different recipes and what are the different techniques that's been used in today's large language models. But yeah, we'll keep this short till here and just want to show a generation done here. So we start with some ID. Okay, this ID here is a 0. It's just a 0 tensor. So 0 in our 65 vocab size, 0 was the new line, dash like /n, the new line, right? So we start with a new line and we ask the model to generate 100 tokens after the new line, right? And then since it's gonna be returning some IDs or integers, we will gonna be decoding it using the decode int function that I showed previously, right? So it's gonna return something like this. This is complete gibberish. Why? Because the model was not trained. It's like very simple model. There's nothing fancy going on. But the point is, given some token, it can predict the next token. Okay, that's all that's happening right now. Great. Now, as I mentioned previously, that the token embedding table in our simple bigram language model has some weights, right? So I showed that it has some weights, and weights are basically a way. I mean, yeah, it has some weights. So obviously, we can optimize the weight using a back propagation algorithm, right? So that's what we're going to do. We're gonna write a very simple training loop, and we're gonna train the model for few number of iterations and see if that improves the generation of the model. Right, so this is the wait, and let's like try to run it. I showed the generation. This is the generation from an untrained model, complete garbage. Now, for an optimization process, we usually initialize an optimizer like an Adam W or an Adam or a SGD or something else of your choice. And this is a simple training loop. So we iterate through, say, 5,000 steps. We pick the batches. So we get a batch of batch size 32. We pass it through the model. We compute the loss, and then that's all. Like and this is like simple. Like we make the optimizer to have 0 gradient at every step. Then we backpropagate the loss that we compute here through the whole network, and then we optimize. And these are like things that you see in any regular trading loop that's been written using PyTorch. You can do the same thing with TensorFlow, but the point is, it's like running, and you can see that the loss is going down. Like it started from 4.5125, and it has gone down to 2.5047. What it means is the embeddings or the representation for every token that was taken care of by the embedding layer, it has optimized to represent each tokens better at this stage. And that's why the loss has come down. That means that given the logics and the target probability distribution, the distributions are kind of closer to each other than an untrained model, because then the loss was 4, now it's 2.5. Great, let's see let's look at the generation. Yeah, like we can see some like a bit Shakespeare style, because earlier the generation was like nothing, so just generating some random gibberish. Now it has some flavor, like we can see V, far, B, it's still garbage, but still better than what it was back then, right? So obviously an optimization helped in this case. Now this is like a simple function. I will not go through it in detail, but basically here, the loss that we are printing is after every step. Like for a given batch, whatever loss was computed, we return back. This is not a good way of computing or visualizing the loss, because at some time, a batch can be really bad for the model. Okay, it can be a very hard batch, and you will see the loss to spike up. right? So we usually compute loss over some eval iterations. So in this case, if you see the eval iteration 100, so it's going to be picking 100 batches, both in the train set and in the validation set, and computing the losses for that. And then, yeah, like getting the mean of those 100 batches. And every batch is of batch size 32, right? So the loss here is going to be a more refined thing, because in those 100 batches, there might be a few bad examples, but overall the number of examples should be good enough that the losses will not go like haywire randomly. But yeah, this is just like a way we do things. But let's just train it for 5,000 steps again. Yeah, there's nothing. I mean, it's gonna be the same thing, but you can see the training loss and the val loss, they are kind of going down simultaneously. So it's 3.26. The val loss is 3.2. It's not going far away. So good optimization that's happening here. Great. A simple language model. Some like we prepared the data, tokenized it, have a simple language model, wrote a simple training loop, run through it, and was able to train it. And we were also able to generate something like this. Okay, still not good, but we need to. We can do better. Right. So far, the predictions of every token was done using the last token, as I talked previously, right? So ideally, like when we are talking in any given sentence, we kind of look at the nouns, the pronouns, or the vowels, consonants. Like, I mean, the next word that we say is determined by whatever we have spoken in the past, right? So that's how we interpret, or that's why we say things, that's how we interpret text, right? The next word is dependent on whatever came before that, right? Thus, the model should also have a notion, also should have a way of predicting the next text based on the text that has come before it, right? Which is not happening right now. So we're gonna be using something called attention mechanism, which was proposed in this paper here. Actually, it was not proposed in this paper. I mean, the attention mechanism proposed in a prior papers as well, but they kind of perfected it and built an architecture on top of that. But they propose a self scale dot attention, and there's some fancy tricks involved in this, and I'm just going to be talking about the tricks. Right. But at this, like, just to take a pause here, you can see there are multiple scripts here, V1, V2, V3, V4 till V8. And basically what I have done is, I have basically in V1, whatever I talked till now, like reading the text, getting the unique, the vocab size, tokenization, like some fancy like convenience scripts like getting batches, estimating losses, the model in here, which has the token embedding table, the computation of the loss, etc., etc. And I have just put whatever I've shown so far in this file, and I've instrumented it with weights and biases, so that with every new thing, new recipe that we add to the language model, we train it, and then I can show you all how it helped improve the trading and the validation loss. Because the better the trading loss and the better the validation loss, the better the model performance is going to be, right? So yeah, just something, and like, let me show you. So yeah, this is what, and I trained it with a batch size of 256, and I trained it for 1,000 iteration. So the model saw 256 into 8 into 1,000 tokens. Let's see, into 8 into 1,000. So that's like, some 20 lakh tokens. Great. Right. When I trained it, let's show. We close all. Let's show the V1. So it started from 4.755, and it went all the way down to 3.63, and the val loss is 3.65. We'll focus on the val loss, 3.65. Great. So this is V1. Now we'll introduce the concept of attention, which was the most pivotal thing that has happened in the space of language models in the last 5 years. Like a lot of things has been built on top of attention. So it's a very important concept to understand and learn. And there are really good tutorials out there, really good explanations, both like in the form of videos and the form of blog posts, but I highly recommend you all read the paper. There are some very nice blog posts written by my friend Aritra and Ritvik on PyImage search. You can read those out as well. They are really good. Right. So let's start with a very simple toy sample. So in our case, the batch size was 4. The context layer or the block size was 8, and the number of channel was 65. So the embedding layer, the embedding representation was 65 dimensional, right? But for simplicity's sake, let's take the representation to be 2. So every token is being represented by a 2-dimensional vector. So this is x. In our original example, the x was 4,8,65, but here's, sorry, the original example is 4,8, but we are showing the higher dimensional representation thingy here, right? So this is what we are getting as logits. The logits, again, in our bigram model, the simple model is very simple. It's not doing much. It's generating garbage, right? So we need to improve. And we're going to be fitting the attention layer, attention logic after the logits. So this is a logit with, say, channel 2, right? This is just a toy example. This is of batch size 4, and we are looking at the first batch. So this is what we have right now. Now, as I said, the model so far is just predicting the next token based on the token that is seeing, the last token that is seeing, right? It has nothing to do, the prediction has nothing to do with the previous tokens. There's no way the previous tokens is communicating anything to the first token. As I mentioned, that when we are saying something or when we are reading something, or the next word that we write is depending on whatever came first, came before the last token as well, not just the last token, right? So these are the tokens. There are 8 tokens here. If we predict a 9th token after this, right now it's only been predicted upon this last token, and we want to convey the information from all the tokens to the last token so that the prediction has information from all the tokens that it has seen. A very naive way of doing that, we can average all the information, because an embedding is basically a high representation, aka some information about that token, right? So we can average all the information about all the tokens, and we can say that, okay, the averaged information is the culmination of all the tokens that has come. So use the averaged information to predict the next token. Great, it will help, but it's also a very naive way of doing so. So here is like we are iterating to the batch size, going through each token, and just computing the mean, right? So if you look at the averaged tokens, you can see that the first token here has the information is been represented by 1.9 and 1.4, and in the average one is also 1.9 and 1.4, because again there was nothing before the first token, so the average is going to be the same. But the second token is the addition of this plus this divided by 2. So this is 1.14, and you can see 1.9 plus 0.9 divided by 2 is going to give me 1.4138, right? So again, so after this, we're going to be adding these 3 to predict, to basically come, like this token is the average of the last 3 that it has seen, right? So we're just averaging. Now, I guess most of you are from computer science background and know that this is a very unoptimized way of writing, like doing this computation, like 2 for loops. It's going to take a lot of time, right? So more or an optimized way is to use matrix multiplication, right? Because it can leverage the parallelism and the vectorization of the hardware, and it can just speed up the whole thing. So, and I just I think I also have a good Medium blog post that show like for two loop, like there was, I mean, they did some computation for their use case. That's not the point. The point is when they were using like two for loops, they were taking 33.52 seconds for the iteration for computing whatever they were computing. But when they used matrix multiplication, it came down from 33 seconds to 0.47 seconds. That's like 99% improvement in the speed. And that's why we want to use the trick of matrix multiplication to do this averaging, right? Still, we are doing averaging. So how to do averaging with matrix multiplication? Let's run through that. Let's say we initialize two matrices, A and B. A is of size 3, 3, so it's a 3 by 3 matrix. And B is a matrix of size 3 by 2, so a 3 by 2 matrix. So if you have done matrix multiplication, you know that doing matrix multiplication of 3 by 3 and 3 by 2 will return 3 by 2, right? So how will that look? Let's run through it. So A is a matrix of ones because torch.ones, and this is some random ends. And this is B, some random ends between 0 and 10. All right. So when we do the matrix multiplication, we get 14, 16, 14, 16. Why? Because 1 has been first, every element from this row has been multiplied with every element of this column and summed. So 2 into 1 is 2, 6 into 1 is 6, 2 plus 6 is 8, and then 6 into 1 is 6, 8 plus 6 is 14. And this 7 plus 4 plus 8 is plus 5 is going to give me 16, right? So we were able to sum it. Great. Now there's some function in Torch called trill. So basically what it gives is for this one, like 3 by 3 ones matrix, it just returns the lower triangle. So the upper triangle of a matrix has been turned to 0. So that's what it's doing, nothing fancy. Now, if we do toss.trill, like the A is toss.trill of ones of shape 3 by 3, and we multiply with the same random end, we get something like this: 2, 7, 8, 11, 14, 16. So what's happening here? So since we, again, as I showed, we multiplied every element of this row with every element of this column. So 1 into 2 is 2, 0 into 6 is 0, 0 into 6 is 0, so 2 plus 0 plus 0 is 2. So by doing this, just using the lower triangular matrix, what we are getting is the first element that was in B. 6, and the second element of the computation is 6 plus 2 and 7 plus 4, because 1 and 1, right? So it's 8 and 11. And the next is the summation of all the 3, 14 and 16. So we were able to, using matrix multiplication, do the addition, right? So here we were doing the addition followed by the averaging using 2 for loops. Here we are doing the same thing with a matrix multiplication, but we have only done till summation. So in order to get the average, we're going to be normalizing the A matrix or this matrix such that the sum of all the rows is equal to 1. And this is how it will going to look. So obviously the first row is going to be 1 because the upper triangle is 0, 0. The second row is going to be 0.5 and 0.5, which sums to 1, because you can see it's 1 and 1, right? So when we do this normalization, we get 0.5 and 0.5. And for the third, we get 0.33, 0.33, 0.33, right? And if we do the matrix multiplication after this, we're going to get the average. How? 2, 7, 2, 7, great. 6 plus 2 is 8, divided by 2 is 4. So this is an average, and this is the average. So we were able to do this. Where is it? Yeah, we were able to do this in a very optimized way using this fancy trick. So the trick is to use matrix multiplication, and we are using this fancy thingy called ones matrix, and then we're trilling it so that we just get the lower triangle. Great. So this is the trick Now let's apply the same trick, this trick, to the original example that we used of batch size 4, context length 8, and channel 2, right? So this is what we did initially, right? 2 for loops, we iterated through the batch, we iterated through each token, did the submission, and got the mean. So looking at the first batch, this is what we got. Now let's do that in a few lines of code with this matrix multiplication. Here the torch.ones are like, to showcase, previously I was using 3 by 3, now it's T by T, because context length by context length is going to be your matrix. We again have to normalize it. And when we multiply it, we're going to see that we get the same result that we were getting by using this unoptimized 2 for loops. So this is 0.1027 minus 0.3762, 0.1027 minus 0.3762. Great. So we were able to do this averaging over the tokens. In this case, like if we pick the last token, the averaging was done of like for all the prior token that just seen. So the last token has all the information from the prior token in the form of an average. Again, averaging is nice because you're losing a lot of information, right? An average, again, I mean, and any idea in statistics will let you know that like averaging can be really misleading. Like in many cases, we compute the median instead of the average, because if there are huge outliers, the average is going to give you a very wrong picture and the median might be a better picture. So again, not a very good way of like aggregating information, but we'll go ahead and I will show how it can be improved. But this is what we have right now. Great. Any question so far? If something is not clear, if not, I will go ahead. No, great.
I don't think so. Even from in-person audience, also I guess they didn't have any doubt. So I guess
okay,
you can
cool.
continue. Yeah.
Cool. Yeah, I hope it is clear. Like the crux of the matter is that with matrix multiplication, we can do averaging of a matrix in a very optimized way. Great. Now this is the third way of doing the same thing, but here we'll be using the softmax function. So softmax is what? Exponential of something divided by the sum of all the exponential. That's what softmax is. So let's initialize the ones matrix of shape T by T, so 8 by 8, because the context length is 8. And we just take the lower triangle, right? We get the lower triangle. Great. As I showed, we need to, So we get the lower triangle. Great. Now we create some way matrix here of shape the same, like T by T, but this is zeros here. What we're doing then is, for all the places in the way matrix, in the zeros matrix of shape 8 by 8, wherever trill is 0, so all the upper part of this trill matrix, which is 0, we are filling that matrix with infinity, minus infinity. So this is what the way is going to look after we do masked filling. So the lower part, the lower triangle remains 0, but the upper triangle became minus infinity, minus infinity. Great. So shape of this is what? 8 by 8, obviously. Now, a fancy thing is going to happen, and this is going to be really interesting. So when we do softmax over this, right? And remember that previously, when we computed this, way equals toss, and let me actually show what way looks like here. This was like the second way of doing. Like the first way was for 2 for loops. The second way was matrix multiplication. So way here is gonna look like this. So 1, then 0.5, 0.5, 0. Like this, and then all zeros. Then 0.33, 0.33, 0.33, then all zeros. Then 0.25, 0.25, 0.25, all zeros. So this is like normalized, right? So this is what I mean. Multiplying this with any matrix is going to give the average of the matrix. Great. Now we are doing the same thing with softmax. So we have the trail, we have the ways, which is 0. We fill the upper triangle with minus infinity. And when we pass this through softmax, we get the same thing. So 1, 0.5, 0.5, all zeros. 0.333, 0.333, 0.33, all zeros, 0.25, 0.25, 0.25, all zeros, right? It's the same as what we got here. So we can achieve the same sort of matrix that can, if multiplied with another matrix, gives the average of that matrix, right? We get the same thing using softmax. How is it happening? So like this is a simple, like this is an implementation of softmax. You can check out this report. It was written by like a previous colleague of mine, Krisha, and yeah, she like wrote a very nice piece of how to implement softmaxes in Python. But again, so let's pass 0, 0, 0, 0, like 4 zeros to the softmax. Let's see what we get. We get 0.25, 0.25, 0.25. Why? Because exponential raised to 0 is giving me 1. Then it's summation of all the exponents. So e to the power 0 plus e to the power 0, e to the power 0, this is 4. So 1 divided by 4 is 0.25. Great. So we can do the normalization using softmax. Now, if I change 0 to minus np.inf, which is minus infinity, like we did here, this is minus infinity, and pass it to softmax. If we do the same, we're gonna get 0.25, because exponential of minus infinity is 0. So if we do this, it's like exponential raised to 0 divided by exponential raised to 0, which is 1, plus exponential raised to 0, which is 1, 2, then plus exponential raised to minus infinity, which is 0, and the same 0. So it's 1 divided by 2, which is 0.5. So again, we got that through softmax. I hope I was able to make it clear how softmax is helping with this normalization that we did. Like previously, we did using this division. Now we are able to do the same thing with softmax. Great. Let's move ahead. Now, what I have done here is basically whatever like single line of code I showed, I just compiled them all together here to run it. And you can see that this is same, 0.1027 minus 0.08. The 3 ways of doing the same thing, one with 2 for loops, unoptimized, another with matrix multiplication, and another with the same matrix multiplication, but using softmax to get the weight matrix here. Great. The reason we are doing softmax will come clear when we push self-attention, right? I hope we have no questions so far, because I will just quickly touch upon self-attention. This is the crux of the whole thing. Unboxing of LLM is basically understanding self-attention properly. Right, so this is the example that we have been running with. Now we have changed the channel to 32, just like to show more power or something. But for 832, we do the averaging over all the prior tokens, and we get some output. Great. So far we can say that the weights are not dependent on the data. So imagine, so what I was saying, so you need to predict the next token based on all the tokens that came before that, right? So far we have been averaging all these tokens from the 0th token to the last token, and you're using the averaged information and predicting the next token based on that averaged information, right? The averaging is done with some weight matrix wherein all the weights were same, right? So it's like 1, 1, 1, 1, 1, 1, 1. Like, so all the token was given equal weightage when like the prediction was coming from that average or some sort of information that information was generated with same strength of all the tokens that came before. But that should not be the case, right? Because if we want to say predict a consonant, and that consonant was dependent highly on a vowel somewhere that came in, like in the say the fourth place, or maybe in the first place itself, we need to somehow give that vowel like more weightage to share the information, right? So every token should talk to each other, but the prediction should come from the fact that, okay, this token is giving me the most, most information. Like, let's use that. So like the consonant is going to be predicted from a vowel at some place. That vowel should speak loudly that, yeah, this is where I am, and this is what you should be predicting, because after me, after this many tokens of my existence that came after me, you should come, right? So there's a communication that should happen. That's how we write something. I'm not sure if I was able to explain it better. I mean, Andres did a great job there. You should check out his video. But what I'm trying to say is that so far with this matrix, every token is giving same information to the culmination of information to predict the next token. But that should not be the case. Some tokens should have more weightage than some other token, because that token might be, like, say in a sentence, noun, if followed by an adjective, the noun should get more weightage than what came before that, right? Like, I'm not good with grammar, but like whoever is expert in grammar, you understand what should come after. There's like some notion in English language, right? And so there's like some concept of weightage. So how can we achieve that using something called self-attention? So we basically need a data-dependent affinity. So far, the affinity, like the weightage or the information sharing, was not data-dependent. It was fixed, right? So all the tokens were sharing the same information. It was fixed. It should not be fixed. It should depend on the data, because English is a very rich language, or any language for that matter is very rich. There's a lot of lots of possibilities. So it has to be dependent on the data. It has to be dependent on whatever token came. If it was noun, it was verb, it was adjective, it was a vowel or consonant, whatever. It should be data dependent. Then, so the idea of self-attention is that every token will emit two vectors. Okay, so one is the query vector, other is the key vector. So every token is emitting two vectors. The query vector is basically roughly saying that is basically what am I looking for. That's query vector. That token is saying what am I looking for in the past, in the future. The key vector is saying what do I can. It's like basically saying this is what I contain. I am a vowel, I am a consonant, I am a noun, I am an adverb, whatever. It's saying something that this is what I am, right? So how to then convey this information? A token's query dot product with the key of all other query gives that affinity, which is data dependent. How? We take the so every token is given the query. Great. So we have a matrix of query. Every token is also giving the keys. So if we do the dot product, if you have, I don't know if you have heard of the term cosine similarity. So cosine similarity is like you have two distributions, and if you do the cosine similarity, you can find how similar every entity is to each other. So it's like kind of the same concept, as in when you do the dot product, we can say that the resulting matrix of the dot product of the query and the key gives me a data dependent, because the query and the key matrices will be emitted by the data itself, by the token itself. So the resulting matrix is dependent on the data, and that resulting weight matrix is a better representation of the affinities of each token. So now, by doing so, each token is getting different weightage, and I can show that in numbers. So how to implement that? We basically have some head size. We define three layers: key, query, and value, and these are basically three linear layers. That's it. So we pass the tokens x to the key. So the x or the tokens are being represented as some other vector. As I said, every token is emitting a key vector, and every token is emitting a query vector. So key and query is emitted. We do the dot product, k dot k, or matrix multiplication of k with the transpose of query with the transpose of k. We get a t by t matrix. right? And then we also, and then we do the same thing. We take the lower triangle, we fill the upper triangle with zeros, sorry, with minus infinity, and then we do the softmax. So this is all the same thing that I showed previously, but previously the weight was fixed, it was constant. Now the weight is being derived from the data. So self-attention is basically a way of computing this affinity to predict the next token based on the data that is seeing right now. So let me run this. Now it's not 34, 38, 32, it's rather 4, 8, 16 because the head size was 16. So every layer is now emitting 16 dimensional vector. Okay, so way zero, let's look at way zero. So if you look at way zero, so obviously the upper triangle is gonna be zero because we are not gonna be looking at future tokens. That's why it's zero. But if you look below, this is one, which is obvious because this is the first token. But the second one, earlier it was 0.5, 0.5, and then all zeros. But now it's 0.19 and 0.8095. So the weight is changed depending on whatever the data there was. Earlier, this was 0.33, 0.33, and 0.33. Now this is 0.37, 0.05, and 0.56. Again, the affinity is changed. So now this is a richer representation of the affinities of token or tokens talking to each other. This is a better representation. So right, like if I pick this row here, so the token at this point, the token that we're going to predict might look at something like, 0.4069 and 0.31. Like the tokens present at this point and this point had more affinity than token that's present at like the first place or even the second place. So this is going to be passing more information to the predicted token prediction than the first token or the second token or the third token for that matter. So that's how the self-attention is working under the hood. So so basically this is a communication algorithm, right? We are communicating something that the tokens are communicating to each other. Again, this is position invariant. So attention has no concept of positions, right? So every token is talking to every other token. So we need to provide some positional encoding, some positional awareness. That's like implementation detail. No need to go deeper into that, but this is how it is. And the implementation above is for generation-based tasks where you don't want the token prediction happening based on future tokens. Like we don't want to see the future, we just want to see the past. That's why this is zero, right? So this is zero. That's why this is zero. We just want to see the future, the past. In that, and I also mentioned that there's a decoder block and an encoder block. So GPT is a decoder style network, right? Wherein like a BERT, if you have heard of something called BERT is an encoder style network, and it's highly useful for sentiment analysis or some like text classification tasks, because therein we don't actually zero out the upper triangle. We keep it as it is. We just basically don't use this trill. If I comment it out, we get an encoder block right away. It's just the difference of this trill, which makes encoder and decoder block, because we don't want to. Because in an encoder block, if you're doing text classification, it's totally fine to let the future token talk with the current token and the past token. It's totally fine. We just need an overall analysis. We just want to encode the whole text. So it's totally fine. Right. Again, so you might have heard something called self-attention and cross-attention. So what's self-attention? So the moment we are using, so if you can see here, the same X, so the same data was used to generate the key, the query, and the value. So if we use the same data, it's self-attention. You're attending to yourself. Cross-attention is when you generate the query from the data, the token, but the key and the value is coming from someplace else. It can be coming from an encoder block, or it can be coming from some other block for that matter. So that's cross-attention. Again, like it's just like how you get the information and do the matrix multiplication. Again, folks say that they're kind of hard things, but these are like very trivial things, just given some fancy names. Right. Now we will be talking about like scaling of the attention rate, because if you look at the figure here, right, this is scaled dot product, right? So why scaling is done? K torch run. So let's take a key vector and a query vector, and then we do the matrix multiplication here. This is just me showing what's happening if we scale and not scale. So we are not scaling right now. We are computing this weight. So weight should look something like this. Let's look at the first, because it's a batched thing. So let's look at the first batch. So this looks like something like this. So this is the raw weight. Again, we have not trilled. We have not removed the upper triangle here to minus infinity or like 0. They're not made it 0. This is like raw affinities, right? So if you look at the variance of K, look at the variance of Q, because these are coming from what? Some unit Gaussian, right? So the variance is close to 1. But if you look at the variance of weight, it's 12. So if I just run it again, you might see the variance go to maybe 15 or 16 or 17, right? Because T by T, it's going to give me a variance like this. So we don't want to have huge variance. The variance should be in a range of 0 and 1, because neural networks are more comfortable learning that way. So all this, I mean, this scaling is basically doing the square root of the head size. So head size was 16. So all we are doing is 1 by under root of 16. That's how we are scaling it, because doing so will make the weight matrices variance close to 1, which is a good thing. We want the variance of the weight matrix to be close to 1. Great. And why is that a necessity? It's a necessity because if we do the softmax of something like this, so the numbers are diffused, right? It's like in the range of 0 and 1, close to 0. If it's diffused, we get a very good probability distribution, right, in the range of 0 and 1. But now we are using the same matrix, same vector, and we are multiplying by 8. So 0.5 into 8 is going to give me 4. It's 4. Minus of 0.2 is going to give me what? 1.6, minus of 1.6. So like we have kind of sharpened, and the variance basically tells you that, okay, this is very sharpened, right? So if we compute the softmax of that, you see that for the same matrix, but it was not scaled properly, you get kind of very like not so good, like it has sharpened. So like a very high value, 0.5 was the highest value. It has gone to 0.8 from 0.2. It has sharpened. So the softmax will pick the peak all the time. So it will, the information sharing is not going to be very good. And that's what the authors realized, and that's why they are scaling it. Great. So this is kind of the attention mechanism we implemented. Every token emitting key and query. We do the matrix multiplication of dot product of key and query to get the weight. So earlier the weights were fixed that I showed here. This is the fixed weight. So all the tokens had affinity, like same affinity, and like communicating the same information. But now the affinity has been computed in a data dependent way, and that makes things easier. And that, I mean, this is more aligned to how we conceive text, right? Because when we write something, when we say something, the next word we say is depending on the prior, the words that came in the past. So this is self-attention, right? What I did here is in the script, if you can see, I basically, let's see, yeah, let's go to V3. I basically implemented the whole logic here in this class head. So you can see key, query, value, and then, yeah, doing the computation of key. So X emitting key, the same X or the same token emitting Q, doing the matrix dot product. We are scaling it here, right? then doing the softmax, computing the value, and then getting the result from the attention block. So what we are doing here, so now earlier in the V1 version, I hope I can, in the V1 version, we just initialized the table. We derived the logits from the table. We computed the loss from the logits. So the logit here was just the higher dimensional representation of each token. In V2, what I did was I talked about positional encoding like slightly. So this was me preparing for V3, but I just added another embedding table here for positional embedding. So what is this? So we are basically providing the model the information about all the token, the positions of all the token. So 0 token, we are just providing that this token is belonging at the 0th position. The next token is in the first position, the second position, so on and so forth. Right? And this helps. So another thing I did was here the logits were coming directly from the embedding. So no computation was done here, right? We are just picking the representation itself, which is not ideal. We need to do some computation as well. So that computation is being taken care by this linear layer. So from the embedding, we go to the vocab size. So earlier this was logits, right? Earlier this was logits. So logits was coming from the table. Now this is not the logits. This is some token embedding. This is some embedding. Now we also get the position embedding. We add them together. So position embedding plus token embedding is my intermediate representation of each token's X. And then we do pass the X through this linear layer to do the computation. Like some computation is happening, which basically gives me logits. And then again, the loss function is same, cross entropy, logits and targets, right? So that's like step 2. I trained that as well. Let me show you how it looks like. I know I am kind of rushing right now, but I hope you can see the difference in the loss. So this was the first line, or let me change the color. Good. Yeah. So this color line here was V1, a simple model, which was just using the higher representation as the logits. Now this is doing some computation with the higher representation, plus the positional encoding has been done. But again, that is not helping because still the model in V2 was still translation invariant. It's not still happening. But there's some computation that's taken care by the linear layer, and thus we have a very smooth curve. And this loss is far better. So we started from 0.44, went till 2.5. Now with just that linear layer computation, the loss improved. Great. In V3, we're gonna be implementing the self-attention. So I talked about the self-attention, shared all, give all the, try to explain what different elements are, why we are scaling it, how tokens have been communicated, how the affinity weight matrix has been generated, etc. So this is me packing all of things into a head class. And what we are doing is the same from V2, the token embedding table, the position embedding table, but we are also initializing the head or the self-attention layer. And this is what we did in the last V2, right? We added the token embedding and the position embedding, and we are passing the embeddings to the self-attention head. So we are getting a self-attended information X here, which we pass through the linear layer to get some computation done. That's it. That's changed from V2 to V3. We just implemented or injected the attention layer here. Now, I trained that as well. So you can see that the linear layer, the attention layer basically is helping even further, right? Let me close V1 because that's significant. Let's zoom it up. You can see that the validation loss went from 0.253 to 0.436. So that's an improvement. So the self-attention is helping, but it's not helping a lot, right? We need to do something more. So the authors, basically, if you see here, suggested multi-attention heads. So not just one attention, but multiple attention heads. So in V3, in the version 3, I was just using one attention head and computing the self-attention, right? But with multi-attention head, we are basically breaking the attention into, say, 3 or 5 or n number of attention heads, and we are then parallel processing the tokens. It has shown to improve the result over just a single head, right? So this is in V4, we are just implementing this attention head. All we are doing is creating n number of heads. N head, I guess here is 4. So we have 4 heads. Earlier it was 1 head. Now we have 4 heads. Right? Again, earlier the head in V3 had an embedding. So like it has the size, or the head size was 32. But right now the head size is the head size is 4. Sorry, the head size is 32 divided by 4, because there are 4 heads. So every attention, so as I said, we are basically breaking one single attention head into 4 attention heads, so that we can do 4 different parallel processing. And thus every head has the head size of 32 divided by 4, which is 8, right? So the size is the same. Earlier it was 32 single head. Now it's 4 heads with size or head size of 8, right? So same thing, but 4 different processing. So will that help? Like just one simple change from 1 head to multiple heads. Let's look at V4 trading. And obviously we can see it went from 2.43 to 2.36. So it's helping. So multiple heads are helping, right? Great. So this is another trick that we use in language models. Let's go to V5. So this is good, great and all, but the authors also, okay. I guess we only have 5 to 10 minutes, but I think I will be able to cover that. Do we need time for Q&A as well? Okay, so we talked about the multi-head attention, basically 1 head to 4 heads that I showed. Now, they also did some feed-forward error. It's just a simple feed-forward or simple multi-layer perceptron layer, like a linear layer followed by a non-linear ReLU activation. So this has been implemented here. A feed-forward network is nothing but a linear layer followed by ReLU, right? So earlier we were just doing the multi-head attention. Now we are computing the attentions and we are passing through the feed-forward network. That's it, just one change. So what's actually like from a layman word, what's happening is in V4, in the earlier, where we were just computing the attention, we were not allowing any computation to happen after the tokens talk to each other. Now the tokens talk to each other with the feed-forward network. What's happening is once the tokens talk to each other, now they are doing some computation with this using this feed-forward network. So it's like, I don't know, recipe or fancy trick that the authors implemented, and obviously it's gonna help slightly. Yeah, it like helped from 2.361 to 2.337, so 0.03 drop in the loss. Great, some progress there. Now, again, talked about attention, talked about breaking a single head to multiple heads, then talked about feed forward. So after attention is been done, using a feed forward network, a simple linear followed by a ReLU activation, we are allowing it to do some communication. Great. Now, if you see here the architecture of this decoder block, you see that this is a block, right? And this block has been repeated n number of times. N is usually 8 or 16 or 32, but n number of times, right? So inside this head, we have some attention. We have the feed forward. We implemented this as well. And you can see some skip connection as well. So like whatever information was here is been passed and added to the information that was generated after the computation. The skip connection was introduced in the paper ResNet. So that was back in. So ResNet is basically, if you have ResNet, is basically you do some computation and then you basically add the computed information from the skipped information, right? You skip it, add it back. So what happens is when you are training a very large model, actually I will talk about skip connection maybe a bit like in 2 minutes right now, but we basically implemented block here. So basically block is encapsulating the attention head and the feed forward, right? So one block will have attention followed by feed forward. And we initialize 3 blocks here. Num block is 3 here, so there are 3 blocks. So earlier in V5, there was just 1 block. Now we have 3 blocks. So if we train with 3 blocks, we might think intuitively that the model should get better because the model size became bigger. But did I get V5? Yeah. Sorry. Let me turn this on. V6. So if you look at V6, this yellowish orangish line, so it's actually giving a bad result. So we made the model bigger, and this is now we coming towards the large aspect of language model. So we talked about a language model, we talked about attention, and we're coming to the large aspect. So as we scale the model will not just get better. We need to apply some good, like we need to apply some optimization, like some tricks, implement some recipes such that when we scale it up, it doesn't give worse performance. So you can see the performance actually get worse compared to V5. V6 got worse than V5. It even got worse than V4, right? It's close to what it's close to V3. Yeah, not good. So we can do better. So one trick is the skip connection, so the residual connections. Another trick is the use of layer norm. So not sure if you might have heard of batch normalization. So you get the batches, there's a batch norm layer, it basically normalizes batch-wise the information. It's really useful for computer vision tasks. But in language, the batch norm is not going to help. We don't need to let chunk 1 talk to chunk 2, because when you think of normalization, it's like some information will be conveyed, right? So rather, we normalize in the chunk itself. So we normalize row-wise rather than column-wise. We don't normalize batch-wise, we normalize the sample-wise. Wait, let's go to V7. And I think here I have implemented residual connection. So as I said, there's a skip connection, right? So X has been added back with the computation that was done with the self-attention. And then again, the same information was added with the computation that was done with the feed forward. So a skip connection is added, and that will obviously help. So let's look at V7. So yeah, whoa. The loss went down all the way from 2.3, which was the best, to 2.082. So that's a huge reduction in the loss, and even the optimization went smoother, right? So it's a big compare to V6, which was our scaled model or the language, like large language model. So you can clearly see that just by using the skip connection, we improve the performance of the model. It's able to optimize better. Great. Another thing that they used was layer norm that I talked about. So yeah, so what they do is, in this architecture, when they do the attention, they do addition plus near normalization. Same, when they do the feed forward, they do the addition and the normalization. That's back in 2017. Now what we do in practice is we first normalize, then we compute, then we add. We do pre-normalization, we don't do post-normalization. So in this original architecture, post-normalization was used. Now we do pre-normalization. So we basically initialize 2 normal layers, and as you can see, we normalize the like row-wise, and then we do the self-attention. Same, we first normalize row-wise, and then we do the feed forward and with the skip connection. So this is obviously gonna help. I mean, the normalization has been applied some other places as well, but as you can see, this is, yeah, this helps. You can see it goes from, what, this is the values, right? It goes from 2.1292 to 2.105, which is great. Now, I mean, these are some of the tricks that I talked about. Going forward, what we can do is stack more layers. So we were just using 3 blocks. We can use 8 blocks, apply some other scaling techniques. And also with language models, the more the size of the context, number of blocks, the memory requirement just grows exponentially. All right, so self-attention requires, like the vanilla self-attention, with the increasing context length of the block size, the computation or the memory requirement grows quadratically, right? So 4 times. So there are some tricks applied, fancy stuffs that's been used to make it linear, such that the attention is linearly correlated with the context length. There are many fancy tricks been applied. Again, it's like a 5-6 years worth of literature. So yeah, I hope this is gonna be helpful. This is gonna help, let me give you some insight about how to build a decoder style language model. And yeah, as I said, encoder is just the same thing minus the trill part, where we make the upper triangle minus infinity. If you don't do that, it's the encoder architecture, and everything remains the same. So that was me trying to unbox a language model. I hope I was able to do an okayish job explaining the whole thing, but I highly recommend you checking out Andre Karpathy's Let's Build GPT from Scratch. I highly like. It's a 1.5 hour video. It's gonna take, if you are very new to machine learning, it might take you a couple of weeks, like maybe a week or 2 or 3 to understand the whole thing properly. If you are a bit like a seasoned practitioner, it might take you a few hours. I went through this twice already, and I might go through it again because it's a very good, and I will try to implement this in TensorFlow and JAX. And this is an exercise to all of you. Whatever you learned today, also do watch this video, and all the credit, like all the code and everything, like I did some modifications here and there, but all the credit goes to Andres here for the awesome talk. It was just me trying to learn and teach, and in the process learn myself. So you do the same thing, you learn and try to teach your friend, or give a talk like this where you teach n number of people, and that way you will gain more confidence into building language models and like understanding the inner mechanism of how things are working. Finally, I will say that just learning how to use ChatGPT is not gonna make you a machine learning engineer. Learning how to use and understand self-attention is gonna make you a machine learning engineer, right? If you wanna pursue machine learning as a career, you need to understand the inner mechanism and not just learn how to prompt things properly. Because there are many ads running right nowadays, and I just don't like those ads. Anyway, I hope that was informative. If you have any questions, feel free to ask me. And yeah, finally, sorry, one more thing. Once you go through his video, Andrew's video, he has a nice repository, NanoGPT. Do check it out. It's a more sophisticated implementation of whatever I showed right now, like because it has like state-of-the-art tricks that we use today, like flash attention, for example, and some other methods that we use to train bigger models. He was able to reproduce a GPT-2 124 million parameter model, and he has to use like 800s 40 GB GPUs. Again, you might not have access to a single 800 at this point. If you're a college student, most probably, you might not have access to that, but you can get away with small language models. And to practice, there are some really nice Kaggle competitions that's going on, especially like Stanford Ribo NASA RNA folding, this single cell. There are some other common lit evaluators. Like there are some really good language model based competitions that's going on Kaggle. Do try to participate with whatever you learned today and whatever you learned from Andrej, and like by implementing all of it. And finally, the exercise for all of you is going to be, this was in PyTorch, convert that to TensorFlow or JAX, and finally use Keras Core, which is a new library, which is like, this is a like very new lab, not very new, it's a new library that's backend agnostic. So once you write something in Keras Core, you don't need to use you can use the same code with PyTorch or TensorFlow or JAX. So yeah, PyTorch to TensorFlow or JAX, and then to Keras Core. Try to, or you skip directly to Keras Core. But yeah, and do try to participate in a competition. Do check out this video. Do check out the repo. That's it. And if you have any questions, you can check me out on Twitter. This is my profile. Give me a follow or something, and just DM me, and I will answer your questions. Or you can just check me out on LinkedIn as well. Awesome. That's it. Will not speak anymore.
And we will bring Ayush again, obviously, because a personal fan of Ayush for a very long time, but didn't able to get connected with him for a very long time. But yes, yeah, thanks for folks for joining here, and see you soon on the next meetup, and we will see you all on DevFest, I guess. So yeah, see ya. Bye bye. Yeah, thanks Ayush again for joining. Yeah.
Yeah.